Hello, and thank you for joining the Health Effects Institute 2020 webinar series. The topic of today's webinar is Particle Components and Associated Health Effects Then and Now. My name is Allison Patton. I'm a staff scientist at HEI. I would like to acknowledge Pallavi Pant, also a staff scientist at HEI, who co-organized today's session. We and the rest of the HEI staff hope that all of you are safe and healthy during this challenging time. As you may know, we are holding 5 webinars in lieu of the HEI annual conference that was planned in Boston in early April, but had to be canceled due to the coronavirus pandemic. We are very grateful that the session speakers and chairs have agreed to give webinars instead. We would also like to acknowledge the hard work of our staff who worked behind the scenes to transform the annual conference into a webinar series. Before we delve into today's webinar, I'd like to make a few housekeeping announcements. We will hold all questions until the Q&A period at the end. All attendees are muted for view only for the duration of the webinar. So please submit any questions you have via the Q&A function at any time during the webinar. You can also upvote questions in the Q&A. If you experience any logistical difficulties, contact us using the chat box, and you can also email us at jkeel@healtheffects.org. After the session, we will make the session will be recorded and will be available on YouTube in the next few weeks. Links will also be posted on our website. After the webinar, please complete the survey. It will pop up on your screen as you exit. And also be sent tomorrow in a thank you note. We really appreciate your feedback. And there's more information on our website about the remaining webinars in the series. So please go there and register for additional webinars later. Today, we will address the question of whether some chemical components or sources of airborne particles are of greater public health concern than others. We will look back at what is known and forward at next steps through perspectives of exposure, toxicology, and epidemiology. Today's chairs are Dr. Frank Kelly and Dr. Jeff Brook. Dr. Kelly is the Humphrey Babcock Chair of Environment and Health at Imperial College London and a member of HEI's Review Committee. Dr. Brook is a professor at the Dalla Lana School of Public Health at the University of Toronto, where he leads the Canadian Urban Environmental Health Consortium, CANU, and the environmental component of Canada's largest birth cohort known as the Child Study. He's also a member of HEI's Research Committee. We have a great lineup of speakers for you today. I will now hand over the mic to Dr. Jeff Brook, who will introduce the first speaker.
Hello, and good morning, good afternoon, good evening to everybody, no matter where you're at. I thank Allison and Pallavi for bringing this session together in HEI. It's my great pleasure to introduce the first speaker, who will provide an overview of the challenges that we face in this topic area. And you've heard from Allison that is Frank Kelly, who's from Imperial College in London. And has had a long career in this area of particle health and toxicology. He has chaired the COMEP, the UK's Department of Health and Social Care Expert Committee on the medical effects of air pollutants for the last 9 years. And as you've heard, he's a member of the Health Effects Industry Review Committee. So I'll turn it over to Frank and mute myself now. Go ahead, Frank.
Hi, everyone. Can everyone hear me? I hope so. Welcome. By way of introduction, I just remind you that particulate air pollution has been the focus of global research effort for several decades now. And I guess the aims have not only been to understand and describe associations between exposure and capability to adversely affect human health, but also to identify plausible biological mechanisms that could explain and support these associations. For me, the story began really with the seminal epidemiological studies in the 1990s, showing a clear association between increased respiratory and cardiovascular mortality and acute and chronic exposure to ambient particulate air pollution. And recently, Pope and colleagues compiled and summarized the findings of 25 years plus of this cohort research using meta-analytical tools, the estimates of the distribution of effects from the cohort studies that are currently available and provide substantial evidence of adverse pollution associations with all-cause cardiopulmonary and lung cancer mortality. And you can see here that for cardiopulmonary mortality, relative risk of 1.13 or 13% increase per 10 micrograms per meter cubed of PM2.5. Now, the epidemiological work has been supported and matched by considerable toxicological research effort to define the underlying mechanistic pathways of toxicity elicited by airborne PM. And again, the lungs and the cardiovascular systems have been very well studied, as we see here in this recent review by Martin Miller, which describes the contribution of oxidative stress to the mechanisms by which inhaled PM induces CVD, and outlines the complex series of interconnecting mechanisms underlying the effects of inhaled PM on cardiovascular morbidity and mortality. Now, health studies describing robust associations between PM and ill health have been contributed by a whole range of organizations, including the HEI with its famous NPAC studies and the ACES study. But we also have the World Health Organization contributing reports in black carbon and ultrafines. And we even have one of our other speakers today who, along with myself back in 2013, produced this review article considering the topic of today's meeting. There therefore has been enormous drive to identify which components could be responsible for the physical and chemical characteristics that are the physical and chemical characteristics which are most harmful to health, and to facilitate the reappraisal of air quality guidelines and standards that prioritize and targeted PM control strategies, I guess, to more effectively protect public health. Now, epi and toxicological research findings have indeed shown that PM mass comprises fractions and sources with varying types and degrees of health effects. But despite this, the question of differential PM toxicity still represents one of the most challenging areas of environmental research. Many PM attributes or components may influence its toxicity. Unfortunately, the current database of experimental and epi studies that are available don't allow us to identify those individual PM characteristics or sources and that are particularly closely related to specific health effects. And it appears that the strength of associations between effects and individual chemical components of the ambient aerosol vary from effect to effect, and that the situation is further complicated by components being associated with certain effects in some locations and not other locations. For example, the ambitious US impact studies that use coordinated toxicology, epidemiology, and exposure research to examine and compare the toxicity of PM components, gases, and sources concluded that the studies do not provide compelling evidence that any specific source, component, or size class of PM may be excluded as a possible contributor to PM toxicity. In the same year, Crowell and colleagues came to much the same conclusion when they said in this article, associations with a given PM2.5 chemical component should be considered as potentially indicative of associations with another component or set of components with similar sources. So given that we've got 20 plus years of attempting to pin down the most toxic components of PM without much success, I can't really see us spending another 20 years in the same vein. Furthermore, as the sources of PM are changing, and hence the balance and components we need to keep in focus, what we're breathing in, and indeed what we'll be breathing in the future, we need to remember that we're moving forward in this respect. And for example, in Europe, non-exhaust PM now dominates transport emissions. So it seems sensible to me that for our future research to look forward, and the differential toxicity of airborne PM is likely to be very relevant in light of the likely shift in composition of PM, composition and the emergence of novel components. And the next few slides, I'll just cover some of these emerging issues. So starting off with the non-exhaust PM. In the UK, we've had a dramatic improvement in tailpipe emissions over the last 20 years. So that you can see now that it's a very small component of the overall PM emission load from a vehicle. And in fact, 60% of primary PM2.5 and 73% of primary 10 now come from non-tailpipe emissions from road transport. And some recent toxicological outputs from colleagues here in London have shown that brake abrasion dust has similar potential toxicity as diesel particles. Here they were considering the clearance of bacteria by macrophages across very low doses, comparing the brake abrasion dust and the diesel. You can see much the same sort of toxicity from the two types of particles. And this highlights our requirement to consider the contribution of abrasion particles to traffic-related clinical health effects moving forward. Another emerging area for us is the realization that there is an ambient component of microplastics, these tiny plastic particles less than 5 micrometers, which consist of either particles or fibers, and they're produced from the breakdown of larger items of clothing, such as clothing, car tires, and mismanagement of urban waste. And given the absolute massive magnitude of plastic production and use these days, this is only going to be an increasing issue. And the evidence that these plastics persist for quite a long time in the environment and even in physiological fluids should raise further awareness about their potential health impacts. Recently in London, we made some detailed analysis of the presence of either fibrous microplastics or non-fibrous. You can see the fibrous type dominate, but of those, when we undertook the chemical analysis, we found up to 15 different petrochemical-based polymers being present. So again, this is an area that's emerging. We haven't got sufficient information on it yet, but we certainly need to do some more research. With the question in mind, are inhalable microplastics, of course, affecting our health? Well, there's some potential evidence there already in the literature. There's a condition called flock worker's lung, which individuals working with flock undergo a persistent dry cough. They have shortness of breath and chest pains. It's an inflammatory related condition, and those exposed to flock-associated dust in occupational settings, it's already been recognized to be a health hazard by the National Institute for Occupational Safety and Health. Moving on then to another potential increased PM emission, and that's domestic wood burning. It's commonplace clearly in residential heating across mid and high latitude climates. Through North America, wood stoves remain most commonly used type of residential heater. And in Europe, we're experiencing a return to home heating with solid fuels owing to their aesthetic appeal and the quest to reduce fuel consumption and combustion. In the UK, we now believe that the domestic sector produces up to 40% of the UK's PM2.5. That's over 3 times more than road transport. And burning of wood is now the largest contributor to PM emissions in the domestic sector. Looking forward, there seems to be this inextricable link between PM and climate change, and we've been hearing increasingly about the contributions of wildfires across the world and desert dust storms. With increased temperatures, extended droughts and high winds and changes in vegetation, there can only be increased risk from PM occurring in increased amounts from these natural events. And as we look at the emerging evidence, we see that there's more epidemiological and experimental data from a growing number of studies suggesting that particles exert a wider threat to human health beyond just the cardiorespiratory systems by negatively influencing a number of diseases, such as adverse birth outcomes, slower rate of cognitive development in children, and accelerated rate of cognitive decline in adults. Right? There remain substantive gaps in our knowledge as to the possible causal pathways for some of these relatively new scientific observations. This could, however, be due to the translocation of the small particles in the overall mix into the target organs, as has been suggested by some researchers. For example, Mayer et al. They have reported the presence of combustion-like particles in post-mortem brain samples, and Bove et al. Reported the presence of black carbon particles in the placenta at both the maternal and fetal side. So the quest to uncover associations between ambient PM and all possible diseases, including prevalent ones but rarely studied ones, has recently been tackled by using a hypothesis-free analysis of large data sets. This particular study here, Wei et al., analyzed more than 95 million hospital admissions of Medicare beneficiaries against PM 2.5 concentrations on the day they presented at the health facility over a 13-year period. And in addition to confirming the previously established associations between short-term PM 2.5 concentration and cardiorespiratory disease, diabetes, Parkinson's, they find that a 1 microgram meter increase in PM 2.5 was associated with over 2,000 extra hospital admissions as a consequence of previously unassociated diseases. And these included various electrolyte disorders, acute and unspecified renal failure, septicemia, intestinal obstruction without hernia, and urinary tract infections. So, as the burden of disease and associated particulate air pollution becomes more apparent, it's ever more clear that there's still much for us to learn. And previous work strengthening the evidence for adverse effects and benefits of interventions tell us that sooner we act to close these knowledge gaps and increase the awareness and development of creative solutions, the sooner we can reduce the public health burden attributable to this complex and insidious environmental pollutant. And with that, I'd like to finish by acknowledging co-workers in my team for many years now, Ian Mudway and Julia Fussell, colleagues in Europe, Thomas Sandstrom, Anders Bloomberg in Sweden, and Fleming Cassis and Bert Brunekrief in the Netherlands. And of course, many, many other great researchers, far too many to name in the time allowed. Thank you for your attention.
Thank you, Frank. It's Jeff here. I see that there are some short questions that are probably ones that can be saved till the end, if their time allows. And I'll turn it over to you to introduce our next speakers.
Thank you. So we're going to have two short presentations next. The first is by Jason Sachs. Jason is a senior epidemiologist at the Center for Public Health and Environmental Assessment in the Office of Research and Development of the US EPA. Jason's project lead for the Particulate Matter Integrated Sciences Assessment He plays key leadership roles in synthesizing the health effects evidence of air pollution for various national ambient air quality standard reviews. Welcome, Jason.
Great, thank you, Frank. I'm happy to be here, and I'm going to briefly touch on some of the conclusions from the particulate matter integrated science assessment with respect to our evaluation of the evidence for PM 2.5 components and health effects. Before jumping into the presentation, though, I just need to display this disclaimer. And so in the 2009 PMISA, this was the first time that we had really conducted a systematic assessment of the evidence looking at PM 2.5 sources and components and health effects, spanning the scientific disciplines that were evaluating the health effects evidence. And based off of that evaluation, we concluded that many components of PM can be linked with differing health effects. And the evidence is not yet sufficient to allow differentiation of those components or sources that are more closely related to specific health outcomes. We further characterized this evidence in a publication that followed the release of the 2009 ISA, Stanek et al. 2011. But what's new since the 2009 ISA? Well, the first is that we had a number of studies that were evaluating PM 2.5 components and health effects using a number of different statistical approaches. I thought that was really elegantly characterized in Mostovsky et al. 2012, where they went through some of these approaches and highlighted their strengths and weaknesses. And then subsequently after this, we had some of the new multi-pollutant studies that were using multi-pollutant techniques to look at combinations of different PM 2.5 components. In addition to that, we had HEI's NPAC study, which Frank mentioned in his presentation. We had a number of single city and multi-city epidemiologic studies that have been conducted, but we had a smaller number of experimental studies, and they were primarily animal toxicological studies looking at cardiovascular endpoints. And so in the process of us thinking about this ongoing review of the particulate matter national ambient air quality standard, in the initial stages, we developed an integrated review plan with the Office of Air Quality Planning and Standards. And within there, we outlined some of the policy relevant questions that we think are important to address, both in the ISA as well as the subsequent policy documents. And one of those pertains to assessing the evidence as to whether the current mass-based indicator is adequate. And so for the context of the ISA, we posed two questions, or I guess scoping questions, that we considered in the process of evaluating the evidence. For studies that looked at individual components, they had to include a composite measure of PM. And by composite measure, we mean PM 2.5 mass that allows us for a comparison of results between the component evidence and the mass evidence. And then for studies that were looking at sources, such as diesel exhaust or gasoline exhaust, but whole source exposures, they had to apply some approach to try and parse out the particle effect. So whether that was using a filter or some other measures that we could compare the health effects that were observed to whole exposures and then exposures where the particle portion had been removed. And so with that information in mind, we consider not only the health effects information, but also the information with respect to how have the ambient concentrations changed over time. And that's reflected on this slide. Where the left-hand side, you see a map of 3-year annual average concentrations of PM 2.5 from 2003 to 2005, and on the right-hand side from 2013 to 2015. So overall, you can see that the overall size of the pie chart has declined, which is indicative of the overall reduction in annual PM 2.5 concentrations. But in the eastern United States, you can see that the yellow portion of the pie chart, which is representative of sulfate concentrations, has shrunken dramatically. And this is due to the almost 65% reduction in SO2 concentrations that have occurred over this time period. So one of the things that we grappled with in assessing the evidence is the fact that when you're looking at the components results, it's very hard to put them all on a forest plot, which is what we've traditionally done, because the different methods are being used. So we tried to devise different approaches to try and visually represent the evidence that we're seeing across these studies and make conclusions. So this is an example from the studies we're evaluating cardiovascular hospital admissions and ED visits. This is a heat map where we try to note the pattern of associations across studies. The different colors are corresponding to the strength of that association, whether it was statistically significant, positive, null, etc. We then took that information and developed these bar charts, which were showing the distribution of associations across the studies that we evaluated to then further allow us to inform our conclusions. Across this, you can see that in this instance, and this is a similar pattern that we've seen for the other health outcomes that we evaluated, but you see evidence of positive associations for the majority of the components that were evaluated, and then you just tend to see relatively consistent and positive associations when focusing on PM 2.5 mass. And so it was the combination of evidence across all the different health outcomes that we evaluated. So we had figures that were similar to that for in each of the chapters within the ISA to help inform our conclusions. And we concluded that many components and sources are associated with many health effects, and the evidence does not indicate that any one source or component is more strongly related with health effects than PM 2.5 mass. And so stemming from our evaluation within the ISA, it led to a series of questions, which I think many are going to be addressed in the presentations that follow, and some are probably good for the discussion at the end. Many are focusing on, how does the fact that we've had limited monitoring of PM 2.5 components factor in some of our results that we're seeing across studies? What is the advantages and disadvantages of the different statistical approaches that have been used? Should some be used more than others? And then the remaining ones, really thinking about, well, how do we move forward? What have we learned to date, and how does that inform our decisions in the future with respect to research focusing on PM components? Is it worth maintaining course, or should we start thinking about shifting in maybe a different direction, still focusing on components, but maybe looking at groups of components and how that's related to sources? So I'm looking forward to the presentations that follow, and I hope we can address some of these issues.
Thank you very much, Jason. We now move on to presentation from Dr. Bruce Copley. Bruce has recently transitioned from industry to the independent consulting realm, following a 22-year career in the US Army and US Air Force as a public health officer and environmental and infectious disease epidemiologist. During these times, or after these times, he accepted a position at ExxonMobil Biomedical Sciences, where he specialized in air pollution epidemiology. And during that time, he chaired the American Petroleum Institute's Health Research Group, which funded several air pollution studies. Dr. Copley was trained in epidemiology at the Johns Hopkins School of Hygiene and Public Health. Welcome, Bruce.
Thank you, Frank. There's the question for consideration here. And I'm speaking largely from my background with industry, and the EPA questions that were posed by Jason are remarkably similar to the questions that industry has had over the years. And there's a few more questions that we would like to also entertain at this moment. So should the search continue? That is the search for a particular set of PM components or species that rises above all the others regarding their potential health effects. If I can advance my slides, here we go. So, HI is not the only institute that searches for evidence of something that we know should exist. Several research efforts have strived to distinguish between those PM species which most strongly associate with health effects from those that really don't. But the findings, as we all have seen, have been highly inconsistent. For instance, in one study, a particular species might show a strong positive association with a particular health endpoint. But yet another study may come along and they observe a null or even a negative association with that same endpoint. So at this point, all PM components are still on the table for determination of which ones are the big threats to public health. And so the search does continue, and there have been, again, many research efforts that have strived to answer the question. So we're still searching. So here are some questions that come to mind for me, at least, is that certainly one signal might be that recent observations at several epi studies at this point, probably going on a half dozen, of superlinearity at low ambient concentrations that might be indicative of relatively more toxic species or types of PM that have been really resistant to or not even targeted in past or current pollution reduction policies and regulations. So maybe these long-standing policies that have targeted industrial and vehicle exhaust emissions have been successful in lowering PM2.5 ambient concentrations overall, but not in the non-tailpipe emissions, some of which Frank mentioned: tire wear, brake wear, domestic wood smoke, also new roadway surface components, or other novel components that persist after those more traditional PM sources are lowered. You can see here in the red boxes that this is part of the curve that seems to be resistant to regulatory policy or action. So the curve has been flattened, so to speak, at these higher concentrations, but yet there seems to be a persistent, dogged, something going on down at the lower concentrations. So perhaps that's the part that is resistant to traditional regulatory policies and actions. So as with the search for intelligent life elsewhere goes on, there's other signals that come out. So you see here that there's regional heterogeneity across all these cross-sectional epidemiological studies. Might also be indicative of varying levels of toxicity among PM components. And so here's one that Helen will talk about later, that you see, significant regional heterogeneity in effect estimates based upon the area of the country. So with all these signals coming in from geographic factors and component factors, are the current data sources that we have and statistical methods, are they still too limited to really process all these signals within a multi-pollutant world? Some more signals. So taking into account that analyses of time activity patterns indicate that most people spend most of their time indoors, even pre-COVID. In some areas of the country and in some homes, the concentrations of indoor generated particles are higher than outdoor concentrations, not only in homes, but in office buildings, subway stations, and other indoor environments. So might the signals from indoor PM be interfering with those from outdoor PM, thus partially obliterating these potentially observable differences in particle species toxicity and in epi studies that's just not showing up in the epi studies? Perhaps that's just interference. So what is the path forward? Jason mentioned several of these. Do we abandon this particle mass-based search? Do we search in other characteristics, for example, particle number, morphology, particle sizes, sources? Do we focus on these new sources mentioned previously by Frank? And can we account for and isolate signals from indoor PM in future searches, distinguish between indoor and outdoor, and sort of try to disintegrate those signals? And are the appropriate data sources, which are really now inadequate, and current analytical tools required for non-mass PM epi research, are they being developed? And do we have the appropriate data infrastructure in place to examine these relationships and trying to, isolate the signal that tells us yes or no? One particle is different from the other as far as their toxicity and their impact on public health. So at this point, I will attempt to mute.
Thank you very much, Bruce. We'll come back to many of those issues at the end of the session. I'm going to pass back now to Jeff, who will introduce our next speaker.
Thank you, Frank, and Jason and Bruce. Some excellent questions posed by both speakers that I hope the listeners online will think about and maybe help formulate some questions for discussion at the end. It's now my pleasure to introduce our next speaker, Professor Randall B Martin, who's now professor at Washington University, also the Arthur B. McDonald Chair of Research Excellence at Dalhousie University in Halifax, and a research associate at the Smithsonian Astrophysical Observatory. His research focuses on characterizing atmospheric composition to inform effective policies surrounding major environmental and public health challenges, such as air quality. His professional honors include selection to the Royal Society of Canada. So welcome, Randall.
Thank you, Jeff, for that kind introduction. And I'm grateful to the organizers for the opportunity to speak with you today and to share with you some of our recent work to integrate information across scales to address the challenging questions of particle composition exposure. And sorry, this is a challenging area with a long and rich history. One could begin with a targeted measurement in a specific location, either an ambient monitor or perhaps even an advanced personal monitor that could offer time series of particle composition information at a specific point that may accurately represent concentrations at that point, but it's confined to that point. To enhance or enlarge the spatial domain, one could turn to a monitoring network, either an existing regulatory network or one designed for purpose, and then conduct a statistical fusion to fill in gaps between those ground-based monitors. And this will increase the spatial domain, but also increases uncertainty away from monitors. An alternative approach could turn to a chemical transport model that could be designed to represent particle composition over a domain of interest and represent that 4D system, but it is a model and subject to its own inherent uncertainty. And there's growing observational information from satellite remote sensing over broad spatial scales, but those satellite observations are primarily columnar, and they tend to be more sensitive to mass than to chemical composition. So the approach I'd like to take today is to attempt to integrate information across these different sources to continue to develop the representation of PM2.5 composition. I'll begin in the area of satellite remote sensing of aerosol optical depth, a measure of columnar extinction due to aerosols in the atmosphere. And then apply a chemical transport model, GeosChem, to calculate the relationship between that satellite aerosol optical depth and ground level PM2.5 chemical composition. Because of the reliance of a model for that calculation, I'll describe the development of a targeted measurement network that's designed to measure the relationship between aerosol optical depth and PM2.5 chemical composition that can be used to evaluate and improve that model representation of key parameters in that relationship. Then the resultant geophysical composition estimates can be statistically fused with ground-based observations from regulatory networks to produce an overall hybrid estimate of PM2.5 chemical composition. Beginning in the area of satellite remote sensing, shown here is aerosol optical depth from a variety of different satellite instruments in the top and bottom rows, and also a simulated component in the bottom right. And I hope it's apparent to you that each of these different data sources have different spatial patterns. And indeed, all of these information sources have strengths and weaknesses that vary with location and vary with time. So an overarching theme of our effort, here led by Aaron Van Dunkler, is to evaluate the quality of these different data sets versus the ground-based sun photometer network of AeroNet that accurately measures aerosol optical depth from the ground. And this enables inversely weighting these different data sets by their relative errors to produce an overall best estimate of aerosol optical depth, such as one can see an example in the center. Now that still leads us with a columnar integrated optical measure. And of interest is the ground level PM2.5 composition concentrations of relevance for health. And so for that next step, we'll turn to a chemical transport model, GeosChem, divide the Earth's atmosphere up into about 1 million boxes to solve for the chemical evolution during transport. You're seeing yellow corresponding to mineral dust coming off of the major deserts in the world, blue for sea spray at high southern latitudes during this month of July, green for organics, largely from fires, also from biogenic sources, black for soot or black carbon, and red for the sulfate nitrate ammonium system. And a purpose of showing this animation is to emphasize the dynamic nature of these aerosol fields in space and time, such that we'll sample the model coincidentally with every individual retrieval from each individual instrument and calculate that local time and space varying relationship between columnar aerosol optical depth and ground level PM2.5 chemical composition. Again, because we're relying on a model for that calculation, we've been developing a targeted measurement network known as Spartan to characterize or to evaluate and improve those calculations. It begins with the well-respected sun photometer network of AeroNet that accurately measures aerosol optical depth from the ground. And in densely populated areas of relevance for health, adds a PM2.5 monitor that's been cleverly designed by our Photon to be highly autonomous and to reduce the burden on the remote operators. Features a removable cartridge with a traveling blank and filters that can be then taken back to a central laboratory and analyzed for the wealth of information about chemical composition that's contained on those filters. The instrumentation package also features a nephelometer that offers a time-resolved optical response, and also the optical information of value to decompose the satellite optical measurements into PM2.5 chemical composition. So at the bottom, you're seeing a decomposition of that relationship. And we've been spending particular attention on understanding the mass scattering efficiency, that relationship between scatter and PM2.5 composition. Turning to the information contained in ground-based monitors about the distribution of PM2.5 chemical composition. At the bottom, you're seeing the bias between the predicted measure of PM2.5 mass and that measured by ground-based monitors, with smooth structures in the east and heterogeneity in the west. And what we've done here, again led by Aaron Van Dunkler, is to conduct a fusion to predict that bias as a function of geophysical fields that affect the relationship between aerosol optical depth and PM2.5 chemical composition. And you're seeing examples of those fields on the right, including subpixel topographical information, as well as some of the more uncertain chemical components that affect that relationship. The result of those different activities yields different surfaces, shown here initially for mass. And those mass estimates exhibit a high degree of consistency with ground-based monitors. The R-squared is around 0.8. But notably, given the geophysical framing of these estimates, that a large fraction of the ground-based monitors, up to 70%, can be excluded for out-of-sample cross-validation, with a reduction in performance of only a few percent. And this implies promise for applicability of this method for species or chemical components with few ground-based monitors. And indeed, that's the case of monitors compared to of chemical composition monitors. They're much more sparse than for mass. Extension of this approach to chemical composition yields the results that are shown here. The performance is better on the left for the secondary inorganic aerosols that exhibit more smooth variation over space and time. And you're seeing, again, these smoothly varying fields that reflect their photochemical production within the atmosphere. On the right, the species that have more of a primary influence, such as carbonaceous aerosols or crustal material, exhibit more heterogeneity. The performance is overall still quite promising, but there's more scatter that indicates the greater challenge in predicting that more heterogeneous chemical components. That's alluded to the earlier speaker, and also opportunities to examine variation across greater in the southwest of the United States, or nitrate is greater in the interior of North America. Seasonal differences over different regions also offer insight into how these chemical composition changes seasonally. And for example, sulfate and organics, both of which are higher in the summer, driven by either photochemical production or greater sources of biogenic carbon. Whereas in wintertime, ammonium nitrate becomes more important for the semi-volatile component that exists more prevalently under colder temperatures. So the earlier speakers introduced the framing of also considering sources, and they're attractive to represent an air pollution mixture, as well as they offer mitigation opportunities. And in order to examine that question, we'll rely more heavily upon the GeosChem model and apply it to calculate the chemical transformation and photochemical production as an air mass is being advected from a source region to a receptor region downwind. And here's some work led by Jun Meng, examines the different sources that contribute to PM2.5 across the United States and Canada. Numbers on the insets show population-weighted concentrations for Canada in blue and for the United States in red. And the panels are sorted by population-weighted contributions to PM2.5 in Canada. And what you can see are 4 sectors contribute roughly equally to the overall PM2.5 burden in Canada. Wildfires dominating across the north, with transportation, residential combustion due to home heating purposes, and industry all playing similar roles. For the United States, we can see some similarities with the transportation and the industrial sectors being quite important, but a more important role for secondary organic aerosol, especially in the southeastern United States, as well as for power generation in the mid-Atlantic region. I sometimes hear concerns that the PM2.5 levels within Canada or the United States are becoming so low that it may be difficult to control their mass further. But I hope it is clear from these pie charts that the ambient PM2.5 within both countries still remains dominated by anthropogenic sources. And even though the sources that have a more natural component, such as wildfires or secondary organic aerosol, also have an anthropogenic component and are relatively modest contributions to the overall PM2.5 mass. Now, also of interest is how the sources contribute to ambient PM2.5 as a function of the ambient PM2.5 levels themselves. And what you're seeing here, as one might expect, is that as the ambient PM2.5 levels increase, the contribution from the anthropogenic sources also increases. And this may have implications for understanding how the concentration response function varies at low concentrations as there's evolution across these different sources contributing to PM2.5. The different sources contributing to PM2.5 also vary seasonally in a much greater sense than PM2.5 mass alone varies seasonally. And I've attempted to illustrate that by showing the dominant sources contributing to summer, or in the top row, or to winter in the bottom row. And in summer, you see large contributions from wildfires, especially in the north and west, secondary organic aerosols in the southeast, and power generation in the east. Whereas in wintertime, the sources are really quite different, with dominant sources from residential combustion for home heating purposes, and from transportation and agriculture get driven by their roles in ammonium nitrate formation and the greater efficiency with that production at colder temperatures. And this may have implications for understanding how these different sources affect associations with a variety of health outcomes. I wanted to show one global slide to put those North American sources in perspective, and here this work led by Crystal Weigel. And I used to think that the burning of solid fuels for cooking and heating was primarily an indoor air quality problem. But I've since been learning about their driving role as a major source of outdoor ambient PM2.5. And here, possibly the largest source, anthropogenic source of outdoor ambient PM2.5. And this is followed by some of the categories that we may hear more about or think more about more intuitively, industrial and power generation sources. Now we heard from Frank Kelly about the importance of metals, and I think we'll hear about that more in the subsequent speaker. And the need to understand the distribution of metals. This is a much more challenging area for which chemical transport models are at much earlier stages of development. But I wanted to give you an indication of some of the surfaces that are emerging for these heavy metals. They still have a great deal of uncertainty associated with them, but it's exciting to have this progress, and here led by Zhenwei Xu. Looking forward to satellite remote sensing, there are exciting prospects to extract more precise and accurate information about PM2.5 chemical composition and its sources. And a couple examples are shown here. First being the Maya satellite instrument led by David Diner. And this instrument is cleverly designed with a broad spectral range with a multi-angle capability and polarization sensitivity that should offer unprecedented information about PM2.5 chemical composition. It's also innovative in being tied to ground-based measurement networks on PM2.5 chemical composition, both Spartan at the international scale, as well as an innovative instrument being designed by John Vulcans at Colorado State University. And on the right, you're seeing an illustration of TEMPO, here an instrument being led by Kelly Chance. And it's part of a geostationary constellation, including Sentinel-4 and GEMS, that are the first instruments designed for the purpose of monitoring air quality and from a geostationary platform, and offering the potential for unprecedented information about sources contributing to the air pollution mixture. I wanted to connect with both the earlier and subsequent speakers in the opportunities and needs to apply these emerging data sets to develop new methods for jointly estimate mortality risk, considering the overall contribution of both the chemical components and mass to the PM2.5 mixture. And I'd like to defer to the other speakers to spend more time on this, but I just wanted to illustrate the opportunities that exist there. So in conclusion, I'd like to leave you with the growing opportunities to apply and integrate multiple information sources to better represent and improve our understanding of PM2.5 composition, and the many opportunities that remain to continue to improve that representation. With that, I'd like to thank you for your attention.
Thank you very much, Randall, for a tremendous amount of information in a short amount of time. I think you've shown that there's incredible ability to resolve spatial and seasonal differences in sources and components now, and hopefully we'll come back to that in discussion in terms of how we can best use that to address some of the key questions we still have. I turn it over to Frank now for introducing the next speaker.
Thank you, Jeff. Our next speaker is Fleming Cassis. Fleming's research focuses on ambient particulate matter and airborne nanomaterials. He's a professor of inhalation toxicology at the Institute for Risk Assessment at Utrecht University in the Netherlands. He also leads the Inhalation Toxicology Unit at the National Institute for Public Health and the Environment, otherwise known as RIVM. He's editor-in-chief of Particle and Fiber Toxicology, past president of the Dutch Society of Toxicology, past president of the Inhalation Respiratory Speciality Section, etc., etc., etc. I think we all know Fleming from his massive contribution to the literature in around particle toxicology. So welcome, Fleming.
Thanks, Frank. Thanks, Health Effects Institute and the organizers for having me on this very interesting webinar so far. I'm looking forward to all the discussion. So I try to shed a little bit different light on what you've heard so far, in the sense that I always look at it that we have epidemiology that provides the wealth of evidence that the air pollution has effects on humans. And as toxicologists, we are asked, okay, is there something to say about the possibility? What are the mechanisms behind it? And we need to separate that in trying to find out how exposure relates to dose, because in the first slide, we always say that the dose makes the poison. It's not the exposure that gives the effect. And then from then, once you know the dose, you can identify what relationship is with health effects. So, and therefore, I think it's crucial always to keep in mind that size is really an interesting aspect in the entire discussion. These typical presentations can be made when you have the software for deposition modeling, where you can see that if you go down in size, that large particles by and large deposit somewhere in your respiratory tract, whether it's the upper or lower respiratory tract. And there is an area where there's relatively less deposition. That means that about everything you inhale, about 80% is exhaled again. And then when you go to the lower size ranges, the efficiency increases again. And here you see the difference also between the deposition in your respiratory tract head. This is typically the red dotted line, what actually can reach the lungs. So size is really an important aspect, and we regulate, of course, PM 2.5. It's interesting that the peak of PM 2.5 is also the area where there's a kind of minimum in the deposition equation. So maybe we should think more about this aspect as well. And to demonstrate that, I think that's very elegant work from Wolfgang Kreiling, Günter Oberdorfer and colleagues that tried to tease out what the role is of the particle size. And they did an elegant experiment with exposing rats to insoluble particles. And then after 24 hours, they tried to lavage the particles out of the lungs and to see how much is in that fluid that you can take out of the lung and how much stays in the lung. And you clearly can see that there's let's say these are the microsine particles. They can be efficiently captured in everything that you take out of the lung, and they are captured in alveolar macrophages, already mentioned by Frank. They're very efficient in capturing particles. But as soon as you go to the nanosized particles, that efficiency is not that great. You see that maybe 20% is actually captured by macrophages. So here you see a biological mechanism that can already explain why particles can be different in terms of their health effects. And the opposite is also true. If you look at how much actually stays in the lung after you wash them, it's the majority is for the nanosized particles, whereas the microsized particles are not well retained in the lung tissue. So the entire story, it's more about toxicity. The deposition clearance, I mean, how fast are particles cleared from the alveolar spaces up to the airways, or are particles, have they a certain size that they can escape mechanisms like the macrophages, they can go into the bloodstream and become more available for other organs, such as the cardiovascular system, or translocated to other organs, such as the brain. So there's a size dependency, and this entire mechanism is for, let's say, engineered particles better understood than we know from ambient particles, but it's a phenomenon that might explain part of the story that we call PM health effects. And again, to illustrate what size is, how important that is, we've done work in Edinburgh with my colleagues there and Edinburgh University, where we exposed volunteers to gold as being a relatively inert, low toxic material. And we did the two different sizes, roughly 1 and roughly 34 nanometer. You can see that the smaller the size, higher the chances that the material ends up in the blood pretty fast after the exposure. It's a 2-hour exposure. And when you do similar type of work in mice, where you can do a larger range of particle sizes, again, you see a particle size dependent translocation into the bloodstream, illustrating that size may be an important factor in understanding why certain particles are more toxic than others. So it's always interesting to look at particles under the microscope. You see all these wonderful different shapes and sizes with needle shape. These are the cuboidals, this is sodium chloride. These are the combustion particles, typical very small particles. But we also have material in there that doesn't look very chemical. So these are the microbial parts in ambient PM, which we don't hear a lot about in the regular literature on PM and health effects. Now, I give you 3 examples which haven't been specifically mentioned yet. I mean, we always have the question, is all PM equally toxic? And one question came up with the measurements that were done around the Amsterdam International Airport, where there was a significant elevation of ultrafine particles in that area. And the question that we've received from the policymakers, okay, are these particles more toxic than the particles from roadways? So the initial work that we've done was done with together with the University of Southern California, where they were able to collect particles near the LAX airport and also in downtown Los Angeles. And we did some very simple, straightforward tests with bronchial cells by incubating them with these particles to see if there's a difference in potency. And in this slide, I show you the reactive oxygen species activity. And there is some differences where the suggestion is that the downtown particles seems to be a little bit more potent than those collected quite near the LAX airport. But it also depends on which indicator you take. If you look at inflammatory potential in these cells, you may see that the picture is reversed, and now the LAX particles seem to be more potent than the particles collected in the downtown area. So these are rather confusing messages that you have for policymakers and regulators, of course. I mean, what can we conclude from that? As I mentioned, these are particles collected on filters. You have a lot of problems getting particles off the filter. So again, we thought, well, let's go back to the humans, because we're not here to protect cells and rats, but eventually human beings. So we took the opportunity to expose volunteers for 5 hours near the airport at a location which is kind of in between the runways and 2 busy freeways. So we captured both particles from road traffic as from aviation. As the Schiphol Airport has a very complicated runway system where flights are going in and out from different runways in different directions throughout the day, we took that opportunity also to get contrast in our exposures. We had 21 subjects that were exposed at least 2 times, some even 5, and we assessed spirometry, exhaled NO, and we measured heart function and blood pressure before and after the exposure to see the immediate responses due to that exposure in a mobile lab. The average concentration in mass are not that high. It's 23 microgram per cubic meter, so you don't even exceed the standards there. There is certainly contrast, but still below the daily standard for PM2.5. and we captured also the gases and particle number concentrations. We used all those metrics to do source apportionment and could identify that the majority of the particles came from departing aircrafts, with somewhat less from arriving aircrafts, and here's the road traffic percentage. But still there was considerable contrast in exposure to particle number concentration to do the health effect assessment. What's interesting is that when we talk about discussions, should we abandon mass as a metric? Well, mass and particle numbers, at least in this study, were actually not correlated at all, whereas for NO2 and black carbon, you see strong correlations. So it may be an independent metric for your analysis. We've analyzed the various health effects indicators, and not all were significantly different compared to in terms of the effect. But for lung function, we saw a small decrease in lung function, which is immediately after the exposure, of course, and a delay in the QT segment in a heart function recording. This was not seen for blood pressure for particles smaller than 20 nanometers. And I have to mention that aviation has smaller particles than particles that are released from road traffic. So the opposite story was seen on for particles larger than 50 nanometer, where we saw a relationship with blood pressure, but not with the other indicators here. To express the complicated tables also graphematically, I thought, well, here's lung function. If you take total P and C, total particle counts, risk reduction in lung function, which is more dominant due to aviation than to road traffic or the urban background. So here we took the advantage of doing source apportionment. And the same holds true for heart function, where actually road particles have a stronger response, a stronger effect on heart function than particles from aviation. Now, the second example is also try to tease out whether there is some differences in toxicity if you collect them from various sources at the source. So here we compared, and the question was, and Frank already raised that issue, with a decreasing tailpipe emissions, we still see that there's a lot of emissions coming from brake pads and road dust, and how toxic is that material compared to the tailpipe emissions. So we've collected it from various brakeware, brake pads. In addition, we also collected wood dust, as again also indicated by Frank. This is still an increasing source for PM in Europe, and we've compared that with a modern stove, but also with an old technology. And another source which is of interest in the Netherlands, at least, is the poultry farms or farms in general. They also contribute substantially to the PM levels in certain parts in the Netherlands. And the last part was tire and road wear. So when you take the very simple assay that was actually, I think, developed also at King's College in London years ago, to look at what the oxidative potential is of the material, which is basically when you we try to find out how much depletion of your antioxidants can be seen if you incubate them with particles. Well, the positive control is a residual oil fly ash. We all know that this is quite potent material. And then we compare diesel and biodiesel, and we see that, well, with biodiesel, there's less vitamin C depletion than for diesel. But if you compare that with the brake pads, you see that the brake pads material is pretty potent in depleting antioxidants, with the exception of one. And this is one which is very low in metals, and particularly in copper. Now, this is not a toxicity assay, but it's what we believe indicative for something what can happen in vivo or in humans in the lung. So as you said, well, we took that material and also to study that in rats by inhalation, being a more realistic exposure scenario, and exposed them to various concentrations. And we assessed what we call the benchmark dose. That is not the no effect level. You need to know for a specific parameter what is the effect that you determine as being adverse. In this case, we looked at inflammatory cells and we said, well, let's say a 10% increase in inflammatory cells in the lung is considered as adverse. Now, if you take all that information and you define and you determine the benchmark dose at 10%, you'll see that poultry farm has the lowest benchmark dose. And I show you only the 90% confidence intervals and not the mean, because it's in fact, you have to consider that entire region. But this is a log scale here. Poultry farm is far more potent than the materials from brake pads, the modern stoves, etc., etc. So this is an interesting observation that although we thought that material from farms would not be that potent, in this case we saw that it was a particularly strong indicator, inducer of inflammatory responses in the lung. And that there is still variability in brake pads in terms of their toxicity. Some are very potent and some are less potent when you test them in vivo. Overall, the conclusion is you can see differences in toxic potency between them from various sources. Now, the last example is bio-PM. I already mentioned, I think it's not well studied in the PM research area, and there's still an interest because of livestock farming to see what it contributes to the total effects. So we collected material from different farms with chickens, with pigs, with goats. And you can see here the composition in terms of how they look like under the microscope. And I think that microbiologists would be quite keen on identifying exactly what's in there. But the general idea is that that these PMs, the microbes that are in those fractions, link to specific receptors on cells and activate an inflammatory response. And when you block the receptors, you can identify which receptor is activated by which PM. So you then get this summary table that for chicken, for all three types of farms, you get an activation of two toll-like receptors, as they call them, but only for pig you see that TLR5 is activated. Now, what does it tell you? That endotoxins, the material is quite rich in endotoxins and lipoproteins, but only in the pig farm you have another source, which is phlegonine, which is also a bacteria. Now, not showing toxicity yet, but we took that material and went to Michigan State University in labs from Jack Hakema and Jim Wagner, and we run exposures there in mice that were either healthy or compromised by pre-exposing them to ovalbumin to create an allergic response. And here you can see the inflammatory response as a function of the dose for the three different farm types. And here it appeared that the goat material is more potent than material that is released from chicken and pig farms. But also, if you compare that with diesel exhaust particles, you hardly saw a response here at the same dose levels as for the other PM. So this material can be pretty active when you inhale it. Interestingly, when we looked at responses in allergic mice, we saw that, particularly for goat farms, the response was actually downgraded and were less evident than in the healthy mice. So to keep things short, I think there's plenty of evidence that not all PM is equally potent on a per gram mass basis, and we definitely need to discuss whether the metric gram is the ideal one. It's probably very easy to apply, but may not be always the best one to tease out what is causing what. There's definitely differences in toxicity among the sources, but keep in mind that it also depends on the outcomes that you're measuring. Sometimes you see that particles from a certain source are more potent in the lung, whereas another source can be stronger in effects in cardiovascular systems. Combustion engines, don't think that they're all alike. We see differences between road and air traffic, most likely due to the differences in sizes and maybe also in the chemical composition. Biological fraction, as I just pointed out, is by and large understudied, but seems to have be very potent compared to diesel particles, for instance. And then risk is, of course, related to both toxic potency and the levels of exposure. So, for instance, for the breakware, the material can be pretty toxic also in rats, but the amount to which you are exposed to might be far less than the diesel exhaust particles. And I don't think that we still need to look for the silver bullet. The source apportionment will help policies far more better than trying to tease out whether it's nickel, vanadium, cadmium, etc. Because in the end, a source can be tackled and abatement measures can be taken from there. With that, I acknowledge many of my collaborators in Edinburgh, in Leibniz Institute in Germany, Rules Kins, Michigan State, Jim Magner and Jack Harkema, but also my collaborators in Amsterdam Hospital for the Human Studies, and Kostas Judas and his co-workers for the source apportionment and supplying us with particles as well. Thank you.
Thank you very much, Fleming. That was a really nice overview of an extensive library of research around PM toxicology. And it was really nice seeing you bringing in some mention of the biological particles, which, as I agree, we often ignore. And I guess part of the reason for that is that increasingly our research is focused in on cities and transport emissions and not those going on in more rural areas. But hopefully we can discuss that a bit more in question time. I'll now hand over to Jeff to introduce our final speaker.
Thank you, Fleming and Frank. Yes, our final speaker is Professor Helen Su, who's in the Department of Civil and Environmental Engineering at Tufts University. She is an internationally recognized expert in air pollution health effects and has led many multidisciplinary teams in environmental exposure assessment and epidemiology over the last 20 years. She also performed advisory work in environmental health for numerous local, national, and international organizations. And she's currently a member, a charter member of the US EPA's Clean Air Scientific Advisory Committee, and also the Institute of Medicine Committee to review the health effects in the Vietnam veterans' herbicide exposure work. She is an associate editor with the Journal of Exposure Science and Epidemiology as well. So welcome, Helen.
Thank you very much. I'm going to share my screen with everybody. First of all, I'd just like to say, start by saying thank you to the previous speakers for their insightful and thought-provoking talks. It really helps set up what I'm going to be talking about today. I also want to just say a quick thank you to the webinar sponsors and organizers for inviting me to speak today. So clearly, as has been discussed earlier today by the speakers, the issues related to PM components and health are complex, and they're not easily simplified. They're growing even more complex over time as the number of measured components, models, and health endpoints grow. And so some of these issues of complexities have been introduced and discussed by our earlier speakers today. And so what I thought I would do over the next 20 minutes is talk about how we can leverage existing and new approaches to advance our understanding of PM components and their impacts on health. So in this regard, I'll use examples from just a couple of studies to illustrate how we can answer questions that have been continually posed. And for this presentation, I've organized these questions into 4 possible scenarios that have been posited over the years. So these scenarios are shown on the right-hand side of the slide. And the first scenario addresses the possibility that a single component is solely or perhaps more responsible than other components for the observed health effects of
Hello,
PM2.5.
Helen. This is
Excuse
Jeff.
me, Helen.
Yes?
Helen, we cannot see
We
your
can't
slides.
see your screen.
You cannot?
No, not yet.
Are you sharing, Helen?
I thought I was, but perhaps I'm not. Okay, am I sharing now?
No, we can't see anything yet.
How about now?
Yes.
Yes.
Thank you.
Oh, yay. Okay, sorry about
Put
that.
it on
everybody.
full screen.
You haven't missed anything, I guess. So anyway, so this is the slide I was talking about. So basically what this slide does is it presents the current understanding that we have of PM health effects and the components on the left-hand side box. And what we're doing today, what I'm going to try to do today is talk about how we can use and leverage existing methods and new approaches to address one of these four scenarios shown here on the right. And these four scenarios have been posited several times across over the years. And the first scenario has to do with the thought that it is a single component or maybe a couple components that are solely or perhaps more responsible for the observed effects of PM 2.5 on health as compared to other components. The second box represents the sources. And so this scenario is that components from a specific source type are solely or more responsible for the effects that we see for PM 2.5 as compared to others. The third is that perhaps the variability in PM 2.5 health effects are due to the fact that there is a non or low toxicity component of PM 2.5 that is responsible for the observed heterogeneity. And the fourth is that there are specific mixtures of PM components that are necessary to elicit an adverse response or are perhaps more associated with that adverse response for PM 2.5. So before I begin to talk about each of these four scenarios and how we can use old and new methods to address these questions, I thought it would be helpful first to frame our current understanding as outlined in the box to the left. So as many speakers have talked about today, we know quite a lot about PM 2.5 health effects. And we know that their health effects vary by region, by season. And we also know that there have been studies of PM components and sources, and these results have not been consistent across study. And so this inconsistency across studies may be due to several factors, but one of the factors that people talk about quite a bit is really the heterogeneity in the PM 2.5 components themselves. So we've known for a long time that the source-related mass concentrations for PM components vary over time, as Frank had discussed and as Jason had discussed. And as shown here on this slide, they also vary over space. So we see here 8 maps of the PM concentrations associated with 8 different sources, ranging from biomass combustion on the top left, traffic, steel industry, metals, coal combustion, salt, residual oil combustion, and soil, shown here on these 8 maps. So some sources, such as traffic, shown here on the upper right, and biomass combustion, also shown on the upper right, are present throughout the United States, while other sources, such as residual oil and sea salt, tend to be more regional in nature. And so we can see that based on the size of the bubbles here, the size of the circles, which represent higher concentrations as compared to smaller circles. And just to note that the bubbles have been, the circles have been sized or scaled according to the contributions for each source. So you cannot actually relate the contributions for each source to each other. Okay. So one byproduct of the spatial heterogeneity in the PM sources and component concentrations is that you get concomitant spatial heterogeneity in the correlations amongst the PM components, which is shown here in this figure. So this figure shows the correlations amongst the daily averages of the many components that are measured at the US speciation sites, shown here in the columns for each figure, as well as in the rows. It does so by region, where we have correlation tables for the West in the upper left, Midwest in the upper right, South in the lower left, and Northeast in the lower right. And the darker colors and the bigger circles represent higher correlations. So the brick red colors in the positive direction, correlations in the positive direction, and the shades of gray, correlations in the negative direction. So it's clear from this figure there are many darker colors and bigger circles in this figure, indicating that many components are correlated with one another, but that the nature of these correlations is complex, varying in strength over time, and as shown here over space. So as expected here for the secondary pollutants, OC, shown the very last, second to last component, sulfate and nitrate are strongly correlated with PM 2.5 in general for most of the regions. However, that this variability is strong for sulfate and OC in each of the regions, but for nitrate, the correlation differs by region, with a low correlation between nitrate and PM in the southern part of the United States. We also see that the correlations are strong between components that are related to similar sources. In this case, in the blue squares, we see the correlations of vanadium and nickel, which are both seen as tracers for residual oil combustion. And we see that even for these tracers, that they are correlated with each other, but the strength of this correlation varies by region of the country, where we see the strongest correlation between vanadium and nickel in the Northeast, which is analogous to what we saw previously on the maps, where oil combustion contributes the most to PM 2.5 in the northeastern part of the United States. We also see correlations amongst many components that have nothing to do with the fact that they share a source or that they comprise a large fraction of the PM. And we show here as just an illustration of this. We see this for calcium, which is shown in this blue vertical rectangle, where we see the correlation of calcium with the various different components for the different regions in the country. And we see that the pattern of the correlations varies substantially for calcium based on what region of the country you are in. So these correlations are important, and the reason I bring them up is they're especially important as we start to look at the results from epidemiological studies, and especially as we look at those results from those studies that are focused on this first scenario, where the aim of the studies are to identify or examine whether there is a specific component or components that are more relevant to PM toxicity than to others. So to help address this question of the single components, there have been several advancements that have been made over time. Most recently, these have to do with issues related to measurements, where there's a number of PM components that are now measured regularly at the PM speciation sites, or that can be estimated using satellite measures. And from both these satellite measures and the monitoring networks, we've been able to develop a series of spatial temporal models to estimate concentrations of the various PM components at specific locations across the US, Europe, and other areas. Importantly, these measured and modeled exposures are now available over sufficiently long time periods, allowing recent studies to examine the harm posed not only by short-term exposures to the components, but also by long-term exposures to many individual components, as compared to previously where we were focused really on just sulfur or sulfate in our long-term studies. So to assess whether there's a so-called smoking gun, silver bullet, studies generally rely on single component models and to a lesser extent on two component models to assess the health impacts of various different sources, various different PM components. Historically, these models have focused on one or a few number of components, sulfur being, or sulfate being the prime component of focus. And typically what the studies do is they use single component models to assess the health impacts of PM 2.5, and now for various components. And this slide shows results from one such study, which is a subset of the ACS study, or the Cancer Prevention Study 2, which is includes about 450,000 adults. And it did so for one outcome, which is IHD mortality, or mortality from ischemic heart disease, which is one of the main causes of cardiovascular death in the United States. They assessed exposures over multi-year time periods for 100 MSAs in the United States, and they used random effects Cox models, adjusting for individual and contextual covariates. And as we can see, results from this study show that in the top row it shows that for PM2.5, we see significant associations between increased PM2.5 exposures and increased mortality from IHD, with a hazard ratio of a little bit less, but of about 1.03. We can also see in the other red boxes the components that were also found to have significant associations between their long-term component concentrations and increased IHD mortality. And these components deal with sulfur and its correlated or related components, selenium and arsenic, as well as chlorine, to marginal extent to EC, to lead, and to iron. And so these results provide some evidence that these statistically significant pollutants are more important to increase mortality from AHD as compared to the non-significant pollutants, such as in this case, sodium, nickel, or organic carbon. And that sulfur and EC are the most important of these components to IHD mortality, given that are observed high hazard ratios. Having said this, though, these findings are not easily interpretable in and of themselves, because there's other factors that need to be considered. So for example, when we interpret these coefficients, we need to consider the impacts of measurement error, as has been discussed before, and also we need to consider the impacts of the correlations amongst the pollutants. So for example, for sulfur, it's not clear whether it's the sulfur itself or a combination of selenium and arsenics, for which it was very associated with, or for example, sulfur, which had a very strong correlation with PM2.5. So it's not clear from this study whether or not the components represent the actual mortality risk from themselves or from correlated copollutants. So these findings are in contrast from another study that was also conducted as part of the larger NPACT initiative. And these findings are from the Women's Health Initiative study, which was also conducted using a nationwide cohort, but instead of for both men and women, this cohort is just of women, and they used spatial models to estimate exposures to PM2.5 and 4 components: elemental carbon, organic carbon, silica, and sulfur. And these components were selected a priori based on their measurements and availability of quality data. So again, these components were analyzed in single component models and Cox proportional hazards models. And what I just like to point out is that the pattern of significant associations differ from that of the ACS, where before we had significant associations with sulfur, silica, PM2.5, and to a lesser extent elemental carbon, and null associations with organic carbon. But now for the WHI, we see the opposite pattern. So in many ways, this is these contrasting results lead us to conclude that there is very little consistency between our findings for the long-term effects of PM components. And this conclusion is reinforced by results from still other studies. And I just wanted to show you those results from one other study. This is for the California Teachers Study. And I chose this study because it also looked at ischemic heart disease as an outcome. And this study is limited to California teachers, again for women, focused on cardiopulmonary all-cause and ischemic heart disease mortality, and examined exposures based on monitoring sites and living within 30 kilometers of such a monitoring site. So in this case, we see that all of the examined components, PM2.5 is a measure of total PM2.5 toxicity, as well as ECOC, sulfate, nitrate, iron, potassium, silicon, and zinc. We see that each of those components were significantly associated with increased mortality from ischemic heart disease. So these results are consistent and contrast with those results that I showed earlier from the ACS and the Women's Health Initiative. And they suggest that there's really not one component that's more important to toxicity than another. So while differences in the study designs and the study populations and exposure may contribute to the observed differences in these studies, the studies together do raise concerns about the robustness of the single pollutant model results with regard to identifying individual components that might drive observed PM2.5 health associations. And so it seems that even if we were to address these issues with regard to study designs, populations, and exposure error, it seems that these single pollutant models, using them alone, that it will be difficult, if not impossible, to overcome issues related to the pollutant correlations. And so that's because the single pollutant models have several concerns that are just inherent to the models themselves. So as shown here on this slide, there are several concerns about single pollutant models that have been mentioned time and time again. So single pollutant models are intended to reflect the association of that component of interest with the health outcome of interest. But in reality, the risk estimate reflects the effect not only of that pollutant of concern, but also of correlated copollutants. And also that many PM constituent concentrations are low, so they have higher associated measurement error, which may result in unstable effect estimates, and thus may affect our ability to detect important associations when they exist. And third, it's difficult to separate the health effects of constituents that comprise large fractions of PM, such as sulfur, from PM2.5. So all told, the interpretation of the single pollutant model results is not straightforward. They are helpful in identifying components that may warrant further study, but because they are unable to really overcome the issues related to the correlations amongst the pollutants, they alone are not going to be able to basically answer the questions that we have with regard to PM component toxicity. And so if we move to the next scenario, where we are interested in examining whether or not certain PM sources are responsible for the observed adverse health effects associated with PM2.5, we can look at the idea that we can group the pollutants by sources to look at their health effects together. And so this idea of looking at sources takes advantage of the fact that we do have correlations amongst the pollutants and uses this correlation explicitly to separate the impacts of the different PM components into the sources. So several methods have been used to examine the impacts of source type. These methods are not used and have been used extensively, especially within acute health effect studies or short-term health effect studies for the sources. But they haven't been used in long-term studies of PM exposures. For the first three, really, because they are, for the first, the source tracers and the back trajectory analyses, it's because they're really not equipped to look at the long-term health effects. But that source tracers really are just another version of the single pollutant models that we had just discussed. And so they do suffer as well, perhaps, from correlations amongst the pollutants. The source apportionment methods have received more attention in the long-term health effects studies, and they've been used in short-term studies, but also more recently in long-term health effects studies to group pollutants into factors based on how they covary from day to day, with these factors equated to common PM sources. In this way of taking advantage of the correlation amongst the pollutants, they actually use what we know, which we saw previously as a limitation in the single pollutant studies, and they use this to take advantage of our ability to combine the PM components into different sources and to examine their adverse health effects. And so this is a slide that shows results again from the ACS 2016 follow-up study. And the results are shown here now not in for the specific components and for PM2.5, but now based on the different source categories that the ACS study identified. And it did so for 8 sources that were identified, including biomass in the top row, coal, steel, oil, salt, traffic, metals, and soil. And it shows the hazard ratio in the 95% confidence interval per IQR increment for each of these sources that have been identified. As evident from the hazard ratios and their associated confidence intervals, which do not include 1, both the long-term exposures to coal and to metals were significantly associated with IHD mortality, and traffic was marginally associated with IHD mortality. Associations for the other identified source categories were null. And these findings largely reflect the associations for the individual components shown previously, where this hazard ratio for coal really reflects the mean or the average of the hazard ratios for the tracers that inform the coal factor. Now we can compare these findings from the ACS to those from one of our recent studies of over 15 million US Medicare beneficiaries in the United States, in which we use similar methods and similar databases to assess the source contributions. And again, for sake of comparison, we divided these source contributions into 8 factors that were identical to those identified in the ACS. And so as we compare the associations from the US Medicare beneficiaries, which represent now a much larger population of about 53 million people as compared to 450,000 people, we see a slightly different pattern in the associations between the sources and IHD mortality. And in this case, what we see is we see significant associations between many sources, most notably coal and traffic, but we also see associations for metals, just as seen in the ACS, as well as soil and oil combustion. So our significant associations for some of the factors, such as oil and soil combustion, and may be due to the fact that we have a much larger sample size. And this allows us to detect associations between these smaller sources of PM2.5 as compared to studies based on smaller sample sizes, such as the ACS. Nevertheless, the findings from both studies, both from the US Medicare study as well as the ACS study, largely reflect the associations of the specific components that inform the specific sources, such that traffic reflects the average of the specific sources that inform the factor for traffic. So findings are useful in that we are not as concerned about the correlation amongst the pollutants when we look at sources. And so, but they have a competing concern, whereas that it is by reflecting the average of 2 components that reflect that factor, it may be that we are possibly washing out the strong health effect associated with one component with that of another, just simply because they come from the same source type. And so now if we move to other scenarios that also benefit from this idea that we can use the correlations amongst the components to address questions related to mixtures. So several such methods have been applied, and this is really probably the area where there's been the most innovation or advancement in terms of methods in approaching the questions surrounding PM components and their health effects. And given the difficulty of observational studies from addressing the correlations amongst the pollutants explicitly, these methods tend to be more statistically heavy or computationally heavy, in that they try to explicitly address the correlations among the pollutants, either by leveraging them in the case of the residual-based method, or by otherwise incorporating them into their calculations of risks and hazards associated with the PM components. Now, the important thing of these methods is they have been developed, and the important thing is for them to be useful within the larger epidemiological world. They must be validated, and they must be easily and efficiently applied to epidemiological data sets. And this has been a limitation of them in the past, where they cannot be widely applied in multiple studies. And then further, they have to produce results that are readily interpretable to the larger community. And so today what I'm going to do is, yes?
Frank here. I'm sorry, we're running into question time.
Okay.
So
let me just go through them, just go very quickly through these two. So one is the residual-based method, which basically takes the residual of one component. It takes the regression of PM 2.5 on one component, takes the residual, and uses that residual to look at the health impacts of a PM. And so you can see here in this figure, which is based on the US Medicare data set, we can see that when we do that, we can see that the non-traffic PM is significantly associated for the cardiovascular, but not the respiratory mortality, and that these risks are differ from those of total PM. And I just want to show this for the Bayesian kernel machine regression, which is a new method for which an R package has been developed and which has been validated. And basically what it allows is nonlinear, non-additive results. So you can model multiple components at the same time in a nonlinear and flexible fashion. And these are just results to show what the results can be and how easily interpretable they are. And then this is just a summary of what I was saying. So happy to address questions. I'm sorry I went very quickly through the last part of the presentation, but we can address some of that in the question and answer period.
Apologies for interrupting. Over to you, Jeff.
Okay, yeah, thanks, Frank. And thank you very much, Helen. It's a very challenging range of material that we tasked you with trying to cover there. So I really appreciate what you pulled together, and it will lead to lots of discussion. Overall, I think this session was great. We did get quite a diversity of input from the speakers across the different approaches to studying this challenging problem, and a range of questions have come in. Several have been answered, I think, online. Kind of overall, I took away from hearing Frank talking about, yes, it's a 20-year journey, and we want to spend another 20 years. And raise a very important point that PM is changing, has been changing, will continue to change, maybe even more rapidly. It's an important point. Jason pointed out that it's still difficult to pick on any one type or source or even to rule them out. Bruce raised the issue of interference, and even again back to questions about indoor exposures. Randall showed the great ability to spatially and seasonally resolve components now and source contributions, and what opportunities that might bring up. Fleming came back to say it's really key that we tackle sources and not components. But it's a very important point is that you may get different answers depending on the outcomes that you're considering. Very challenging. Helen came back again to talk to us about the importance of looking at sources. So that's my quick recap. I want to have some time for discussion over the next while, and as I've looked at the questions, I've seen that they've come through a number of different sort of realms of areas. And let's picking up on that sort of last point about the endpoint or the outcome you're studying and how that could lead to different rankings and sources. And so Estela Blanco asked a question about how it appears that many of the things we've been talking about have been linked more to mortality and cardiovascular disease, but are there differences in how we might think about what sources are important with respect to adverse birth outcomes? So maybe I first turn to Fleming to see if he has any comments on that question around different outcomes, like in this case, birth outcomes, of which I know there's another question about exposure time windows too.
Oh yes, if you compare what can happen in the lung and what can happen in terms of birth outcomes, I mean, in order to see differences in effects on birth outcomes, it seems that your particle needs to travel a long way to get to the placenta and then to the fetus. So this is a size aspect, and we do know from work that we've done with diesel and pregnant rabbits that very small particles actually can reach that area and can be transferred into to the fetus, where large particles, microscale particles, typically what we call PM2.5, do not. This does not rule out that large particles do not affect birth outcomes, because you can still have a secondary effect where something happens in the lung, like a specific inflammatory response leading to something on the cardiovascular system, which then impairs the placenta function and birth outcomes.
Thanks, Fleming. And you brought up inflammatory markers. So there were a series of questions around sort of linking some of the toxicological endpoints to humans and then to epidemiology. Any thoughts as to whether or not certain cytokines or inflammatory markers or other markers might be the ones that are most linked to what we observe in epidemiology, like mortality? Is there something simpler in that realm that might tie tox and epi and humans together? I know that oxidative potential has been a common marker people have used, and you showed some data on that as well. And Fleming, you can maybe comment, and then please Frank and others.
So very briefly, I think what you need to understand what the entire line of events is that will lead to this measurable adverse outcome, like lung cancer or anything like that. And the things that we measure in toxicology, particularly in vitro, but also in vivo, are kind of indicator for something which can happen if the entire adverse outcome pathway is followed, and we only measure at the beginning of that. So it's not that we can always say if we have this cytokine and we measure an increase of 25%, that will always be very predictive for let's say fibrosis in the lung or something like that. Unfortunately it's not that simple. You need to have a bunch of measurements and a good understanding of the mechanism of action, the mode of action, and to understand what adverse effects you actually can predict with the toxicological data.
Frank, follow up on that?
Just expanding on that. If we remind ourselves that it's long-term chronic exposure to air pollutants, which contribute to the development of a whole range of different diseases and conditions, and the commonality that seems to occur is that yes, oxidative stress and inflammation are common pathways involved in the generation of a lot of involved in a lot of the mechanisms which are involved in the development of these conditions. So which cytokines? There's a whole range of different ones which seem to come in. Some of them very early, some of them very much later. But I think the issue is it's the ongoing exposure on a nearly daily basis over many years, which finally leads to the disease development.
Oh, thank you very much, Frank.
Yeah.
Hopefully that has broadened some of people's thinking in this area. Another sort of topic area I've grouped some questions into around new sources or PM types. Frank mentioned how things are changing quite a bit, and that ranges from plastics to maybe greater recognition of the biological constituents on particles. So there's some questions about plastics, which is a very topical one around how they stay how long they stay in the air and how they're measured. Quick follow up on that, Frank, you can provide?
Yes, thank you. They seem to be quite buoyant, but ultimately this will depend on their size, their composition, and of course the weather conditions. But there have been studies, I think last year, which suggested that there were particles found in very remote places such as the Alps, which looking at the back trajectories probably had originated many hundreds of kilometers away. So yeah, we think that these particles have the ability to travel very long distances.
Okay, great. Okay, thanks. Also on sources, it was brought up in a couple different presentations, was around non-tailpipe sources. And that brings us into the realm of metals and also the interaction of metals with maybe acids and other things in the atmosphere. Is there any sense as to amongst those sort of a rising prominence of say non-tailpipe versus new sources like plastics or agricultural related particles? What might be a greater priority? Another sort of new type of particle, or not new, but new source, is the rise of the gasoline direct injection engine emissions. Any sense of a way to sort of start to prioritize these and move forward that anyone wants to offer?
If I could just interject there, I think some of the data that Fleming showed, especially around the toxicology of the different brake pads, is quite fascinating, because we know that they are a major source now of metal-laden particles in cities. And there was one brake pad there which seemed to be, you know, very, very non-toxic. So, I mean, I think, you know, understanding what that brake pad is and having those discussions with industry might be, you know, very, very important as we move forward in our city transport systems.
Yeah, I mean, it points right towards solutions right off the bat. Other perspectives from our speakers about some of these new sources or sources of rising prominence that we may want to prioritize or think about solutions?
I mean, I think this is Helen, from the epidemiological perspective, it takes some time to be able to collect sufficient data to address some of these emerging pollutants or new pollutants that might happen. I think that there are clues that things like the brake pads, for example, might be important to toxicity when we look at the different hazard ratios associated with different sources and associated with different health outcomes, and also the different components, where they show that these certain metals show up repeatedly as significantly associated with an adverse health effect. I mean, I think I showed results for IHD mortality, but if you look at the wealth of health outcomes that have been studied, including birth outcomes or different sources of hospital admissions mortality, that those influences of brake pads and other new emerging sources are starting to be seen.
Okay, great, Helen. I know we're running really short on time, and we could probably discuss for a long time on these questions. In one other area that I noted of interest was around improved study designs to capitalize on differences between cities, capitalize on what now is resolvable through some of the methods Randall presented. And unfortunately, we don't really have time to get into ways to sort of summarize all of that. So I better recap before we finish. And again, I sort of summarized some of the key things that I heard from the speakers. You know, one of the areas I think that's really important for us to still recognize is that generally, you know, half the mass of PM is secondary. And we don't really have a lot of options to really specifically examine the importance of these different secondary types or link them to sources. Perhaps the models like Randall suggested can resolve some of these, might help show us a path forward in that area. So that's an important consideration. You know, we're still getting down more and more as some areas get lower in PM that we need to start to think about prioritizing certain sources that might be more harmful, more toxic. But we often, I think, need to ask that based on location, since it really does differ by location as to what are the levels or what are the sources, and considering more what can be done versus what we should be doing. Sometimes there are some low-hanging fruit that's always worth focusing on in that sort of realm. I see that now we're really out of time, and I really appreciate everybody's patience and attention to a great series of lectures from our speakers. I wish everybody a great final bit of their Wednesday or possibly even Thursday, and I turn it over to Allison and HEI to close.
Thank you, Jeff, and thank you all of the speakers and also Frank. This has been an excellent overview of what's known about PM composition and health effects. Just for a few logistical questions that were coming through on the Q&A. The webinars will be made available, both the videos and the slides will be linked on our website. Someone asked about ultrafine particles. You can learn more about that at the next webinar in this series on understanding ultrafine particles in health. How can we make progress? That's on May 5th, 2020. Please register and join us if you are interested in that topic. And after you close the webinar, there will be a post-webinar survey. We really appreciate your feedback. So thank you again for joining us. This particle composition is a challenging and important question, and thank you to the speakers for raising a number of different approaches to answer this question. We look forward to seeing where this work takes us in the future. Thank you.
Thank you.